photo I got here to go from Susanna. The title of today session. Okay, so I'm going to present a gentle overview of the things connected to divisibility property of channels and dynamical maps. So I briefly recall you basic notions related to linear maps like positivity, complete positivity, Schwarz property, etc. Then comment on divisibility of quantum channels. Then review, main topic of my presentation, which is divisibility of dynamical maps, in particular, so-called CP divisibility, which is very much related to the very notion of quantum Markovianity. Then I generalize a scenario going from maps to quantum processes. Then I plan to say a few words about Markovian processes, classical quantum processes, which can be interpreted as classical stochastic processes. And then I will try to illustrate all these notions, just presenting two paradigmatic open quantum systems, so-called spin boson model and pure dephasing evolution. Okay, so majority of my talk is in majority of my talk I use only finite dimensional scenario. However, a lot of results can be generalized to infinite dimensions as well, but still there are several problems in infinite dimensional case which are very hard. I will comment on that. So let me start with the very basic notion of positivity. So consider a linear map from B of H to B of H, and such map is called to be positive if it sends any semi-positive operator from B of H to semi-positive operator. So very simple definition. And then we have generalization to so-called K-positive map. So we extend original map by K-dimensional identity. So this is an identity map acting on a algebra of K by K complex matrices, right? And we call original map K positive if this extension is positive. And eventually we call it completely positive if and only if all K extensions are positive. And if we work with finite dimensional Hilbert space, then as we know, due to very nice observation of choice, and this hierarchy of conditions saturates with D positivity. So the map is completely positive if and only if it is D positive, where D stands for the dimension of the Hilbert space. Okay, so let me illustrate the difference between completely positive and positive maps just using this very simple qubit example. So as you know, in the qubit case, any density operator can be represented using famous block representation, like follows, that is identity plus block vector times the vector of Pauli matrices. And let me consider a map which is unital. And such map induces a map on a block vector, right? So this map can be represented as a linear map sending block vector into. So this is a linear map from R3 to R3. So let me consider three very simple maps. the first map just changes the sign of second coordinate. Second map changes sign of all coordinates, and the third one changes the sign of first and the third. Of course, all these maps are positive because, well, if you start within a block ball, you stay within a block ball. But so they are trivially positive. And I guess which of them is completely positive?
The only
Third one. Yes. This is transposition because, well, it changes the sign of x2 when we transpose sigma y goes to minus sigma y. The second map is a famous reduction map, very well known from entanglement theory. And only third map is completely positive. So, you know, maps which are very similar, right? In this picture with block representation, actually, they're quite different. Two of them are only positive and only one is completely positive. Okay, so for us, maps which are positive and trace preserving are very important. Completely positive and trace preserving, well, we call them CPTP. Unital map with obvious property. A dual map where the duality is defined with respect to Hilbert-Schmidt inner product. And of course, we know that a map is positive and trace preserving if and only if it's dual, it's positive and unital, right? Okay, and positive and trace preserving maps enjoys well-known contractivity property. They are contractive with respect to trace norm. And similarly, positive and unital enjoys the following contractivity properties. They are contractive with respect to operator norm, right? There's another nice property. Namely, if the map is unital, it is called Schwarz map, if and only if it satisfies this Schwarz inequality, right? And we call it K-Schwarz if this K-dimensional extension is a Schwarz map. And it is again well known that K-Schwarz maps somehow interpolates between K positive unital and K plus one positive unital. So in particular, Schwarz maps interpolates between positive unital and two positive unital maps, right? So Lindblad already in 75 proves that relative entropy is monotonic under the action of completely positive and trace preserving maps. So it enjoys this nice monotonicity property. And this nice result was later on generalized by Ullmann, who proves that actually positivity is sufficient to prove monotonicity. And then Petz observes that we can still relax the assumption, and what is important is that the dual is Schwarz, right? And a few years ago, Alexander Miller-Hermes and David Tripp still relaxed this assumption and proved very, very, very beautiful results that actually what we need is only positivity and trace preservation to have this monotonicity property for relative entropy. Okay, so let's move on to quantum evolution. What we mean by that? We mean a family of maps mapping initial state, so a state at time t0, into the state at the current time t. Right, so these are linear maps defined for any t greater than initial time. And of course, we require that for each t, this map is completely positive and trace preserving. Enjoy this initial condition properties that initially nothing happens. The map is just represented by identity superoperator, and is sufficiently smooth, right? It is, we assume that it is differentiable with respect to time. Well, we have classical analog of this object, so-called classical dynamical map. And this is represented by a family of stochastic matrices. Right? So for any t larger than initial time t0, the map at time t is represented by a stochastic matrix. This is initial condition, and again, we assume that the map is differentiable. And actually, if you have a positive and trace preserving linear map, right, and you fix arbitrary orthonormal basis in the Hilbert space, the corresponding rank 1 projectors, right, and you define this matrix Tij according to this formula. Right, so you perform the trace P of I times phi acting on P of j. Because phi is hermicity preserving, well, phi is positive, so this is positive operator, this is positive operator, so the trace is non-negative, right? And if you sum over I, right, you get identity. So sum over I is just identity, so this is stochastic matrix. So this map, a single positive trace preserving map, encodes infinitely many stochastic matrices. Just any orthonormal basis gives rise to a specific stochastic matrix, right? Okay. So actually, even given a quantum dynamical map, you can produce infinitely many classical dynamical maps according to this prescription. Okay. And as I already said, there is a essential difference between positive and completely positive map. So any positive map can be represented like this with some real coefficients AI. Actually, any map which preserves hermiticity can be represented like this. In particular, positive maps can be represented like this. The only problem is we don't know how to characterize these real coefficients in order to guarantee positivity. And this is still an open problem. And completely positive maps, this is just a very special subclass of positive maps for which all these real coefficients are positive. Then you can immediately define Gauss operators and eventually get this celebrated Gauss or Gauss-Choi representation. Right? So, well, positivity of an operator in the Hilbert space is just, as we know, spectral property, right? We find the spectrum and check whether or not all eigenvalues are non-negative. However, the very notion of positivity of a linear map, it is not a spectral property. That's why the problem of classification positive maps is so difficult. However, the very notion of complete positivity is again spectral property, because given a map, we find a Choi matrix and check for the spectrum. And another thing which is of course well known is that positive maps are not fully compatible with quantum physics in the following sense that if we have a composite system, right, living in this tensor product Hilbert space, and we are given two positive maps, one acting on operators corresponding to subsystem 1 and the second one acting on the operator corresponding to subsystem 2. And when we define a natural map, which is just a tensor product of phi 1 tensor phi 2, then even if phi 1 and phi 2 are positive, the tensor product in general is not positive, right? So quantum physics indeed needs completely positive map to define the proper state transformations and the quantum evolution. And again, there is a well-known scenario which gives rise to completely positive and trace-preserving map. This is a theory of open quantum system when you try to describe dynamics of your system which interacts with another one, which we call as environment. You know the total Hamiltonian of the system plus environment. You define the unitary evolution starting from the product state. This is initial state of the system you are interested in. This is initial state of the environment. You unitary evolve, and eventually you trace out environmental degrees of freedom, and these constructions gives rise to a family of maps parameterized by time, which is completely positive and trace preserving. And usually we call such kind of evolution or such kind of maps just reduced evolution. Okay, in my talk, I will assume that the initial time is just equals to 0, and this two-parameter family reduces just to one-parameter family. Okay. Any questions?
The H is T independent. If you fix T0 to be 0, it's 1H, right?
Yeah.
Isn't H T dependent?
H?
H is T
No,
dependent.
H is essentially H can be T dependent, right? Well, in the simplest scenario, it is time independent, right? You have a time independent Hamiltonian of the system plus environment. This is just H times T minus T0.
The question is whether every open quantum system can be described as the same H. I mean, if I have an H, this defines an open quantum system. We agree on this one.
Right.
Is every open quantum system given by such an evolution?
Yeah. Well,
That's pretty.
if the map is time homogeneous, yes, right. It's just a time spring dilation.
It's just
If
that
the map is time,
here you need infinite dimensions then.
absolutely.
That's the only.
Right, of course. But then you need, in general, infinite dimensional environmental space. If the map is not time homogeneous, well, you need time dependent Hamilton.
And then you can extend further to make it time independent again.
Yes. That is, oh, yes, of course. Okay, and the simplest example of dynamical maps are just so-called Markovian semigroups, which are governed by the following so-called Markovian master equations, where we have time-independent generator, script L, which govern the evolution of your system. Right, so trace preservation of the map is equivalent to this property that the dual of L just kills identity. And now you may ask the question, what are conditions for the generator, which guarantees that when you solve this master equation, the solution lambda of t, which has this simple form, enjoys the desired property like positivity, K positivity, or complete positivity, Schwartz property, etc. So to have a map which is dynamical map which is positive, the generator has to satisfy the following property. For any rank 1 projector, to compute L on P and then sandwich with orthogonal complement, right? And it has to be positive for any P, right? To have a map which enjoys Schwartz property, L has to satisfy following property, right, for any operator X. And as you see, these conditions can be immediately generalized for K positivity or family of K Schwartz maps, right? You simply replace L by K-dimensional extension in this formula, and to have dynamical maps which enjoys, which are K Schwartz, you have to generalize this formula just replacing L by K-dimensional extension, right? The same problem you can formulate for classical evolution represented by a family of stochastic matrices. Again, the simplest scenario is just Markovian semigroup governed by, again, linear master equation. And conditions for this classical generator are very simple. So the generator gives rise to a family of stochastic matrices if and only if off-diagonal elements are non-negative. And trace preservation condition is equivalent to that condition for matrix elements of K. And again, given a generator which gives rise to a family of positive trace preserving maps, right? You can define the corresponding, when you are again fixing orthonormal basis in the original Hilbert space of the system, you can define Kij matrix, and it's almost trivial exercise to check that matrix defined like that enjoys this property. And actually, it was proved long ago by Kosakowski that L generates a positive trace preserving semigroup if and only if for any orthonormal basis in the Hilbert space, this guy defines a proper classical generator. Right. Okay, so eventually we arrive to the celebrated result due to Gorini, Kosakowski, Sudarshan, and Lindblad. Now the map is completely positive and trace preserving, if and only if its dual is completely positive and unital. And actually, this coincides with the property that the dual is D Schwartz. Again, you remember that D is the dimension of the Hilbert space, right? So actually, when you study those two papers, one published by Gorini, Kosakowski, and Sudarshan, the other by Lindblad, Gorini et al. Work in the Schrödinger picture, right? Lindblad work in the Heisenberg picture, heavily used Schwartz property of the map. However, essentially they arrived at the same result. So the generator L gives rise to a family of completely positive trace preserving maps, if and only if it can be represented in this universal form where H is just Hermitian or self-adjoint operator, and phi is some completely positive map. And this is a dual representation, right? So let me comment on GNS symmetry, which was discussed yesterday, right? So suppose that sigma is just invariant state of the evolution. So it is killed by the generator, right? And we introduce this inner product with respect to sigma, or GNS product, right? And this GNS symmetry, in terms of corresponding generator, the property is displayed here, that essentially this map, well, jump superoperator in the Lindblad representation is self-adjoint with respect to GNS inner product, right? This is GNS property. So as you see, if you compute the map, I mean you exponentiate the generator, the map enjoys GNS symmetry if and only if you do not have Hamiltonian part, right? Because Hamiltonian part, well, the Hamiltonian part is not essential for GNS symmetry on the level of the generator. Okay. As you know, the Lindblad worked already in the infinite dimensional scenario. However, he assumed that the generator is bounded. But we know from papers of Alexander Holevo, Aberson, and also Holevo and Reinhardt that there are completely positive semigroups which are governed by generators which are not of the standard Lindblad form. So the problem of characterizing of complete characterization of the corresponding generators in the infinite dimensional setting, giving rise to legitimate completely positive trace preserving or unital my groups is still open. So maybe Reinhardt can comment later on.
So to get the GKLS form, one assumes that there is a weak coupling between the system and its environment, right? So in order to get these, what is different, right? That's my question.
I didn't quite read.
So to get the GKLS form, the underlying assumption is that there is a weak coupling between the environment and the system.
No, you just start from the complete positivity, continuity on the trace class, and completely positive of each of the maps.
These two original papers are purely mathematical results, right? No coupling to the environment like that.
Or be derived.
Nowadays, one talks.
Right. But your problem is what are the properties of the operator which gives rise to completely positive trace preserving map, and you derive the property. Guarini et al. Derived for finite dimensional case. Lindblad derived it for infinite dimensional case, but assumes that the generator is bounded.
And type 1, not arbitrary phenomenon.
Yeah.
Just really not.
And of course, now we know that that kind of evolution you get if you assume that your system interacts with another one environment, but the coupling is weak, and you also require a lot of additional assumptions. All of them can be summarized as, for example, weak coupling limit.
I should say that. Yeah, so this is just one example. I was, but actually I mean, this is not an equal weight thing here. The theory that Arvidsson started, actually, Rajarama is an expert on that. Here, so I'm not the expert here. It's really him, right? And
I should
there's a lot of theory about the non-standard semigroups, but it's so far, I would say, still largely by example. Classes of examples, right?
Right.
But there's no general theory.
Right.
Is that fair to say?
How crazy are these examples? Are they easy to write down, or?
There are examples of semigroups of endomorphisms, where the generators are derivations. There is whole class of them, with Arison, powers and all. Then there are many other examples where you have proper CP semigroups, not endomorphisms, like Franco Paniolo and many others have studied.
So Hollywood's example is a funny diffusion along the diagonal that on a quadrant. It's a very specific example. So
There are many examples motivated from classical probability. So
Tillerson has produced classes of what Arvesen calls type 3 examples, which are like so in Arvesen's like a little bit like von Neumann, right? So with the von Neumann algebra, horrible terminology, have nothing to do with each other, right? So but type 3 was open for a while to even see that they were good examples. And so same with the semigroups here in Arvesen's theory, he just thought there might be something like that. And then Tillerson produced a continuum of examples. Quite impressive. So Tillerson on many counts. Right?
Okay. Are there any questions? Okay, so let me move to the main topic, which is divisibility. So essentially you can study the divisibility of single quantum channel, or you can study divisibility of family of channels, I mean dynamical maps. So let me start with a comment on divisibility of single channels. So suppose you are given a quantum channel, and one calls this channel to be divisible if can be represented as a composition of two channels. But we assume that the channels these channels are not unitary. Because, well, if it is unitary, the inverse is unitary as well, so it's trivially divisible, right? And there is an interesting problem given a channel to decide whether this channel can be represented as an exponential of Lindbladian or GKLS generator. The problem was studied this very nice paper. One co-author of this paper with us, and they prove that this is NP-hard problem. Well, the problem is that of course somehow L is represented by logarithm of phi, but as you know, the logarithm has infinitely many branches, and well, the problem is to check whether there exists at least one branch which is compatible with this very structure of the Lindblad superoperator, right? And recently Mario Zeman and David Davalos published a very interesting observation. They prove that for arbitrary quantum channel can be represented as a composition of, well, Markovian one and a channel which belongs to the boundary, right? Boundary of well, you have a convex set of quantum channels, right? And this phi b belongs to the boundary of this set. Okay, but my main concern is the notion of divisibility of dynamical maps. What I mean by that, suppose we are given a dynamical map, lambda of t, and we call this map to be divisible if and only if the map enjoy the following property for any t and s, well, like that, right?
and lambda t is from B of h to B of h.
Right. Okay, and well, this two parameter family of operators is again from B of h to B of h. Look, if lambda t is invertible as an operator or super operator for any t, then the map is trivially divisible because you can always define this family of operators V as follows. However, if it is not invertible, at least for some t, then divisibility property is of course not in general not guaranteed. So, knowing that it is divisible, what can we say about the properties of this two-parameter family? So we call original map T divisible, T from positivity, if this parameter family of BTS is positive and trace preserving, and it is called CP divisible if V is completely positive and trace preserving. And actually this very property of CP divisibility is usually accepted as the definition of Markovianity of the original dynamical map, and this definition was proposed more than 10 years ago in this paper by Susanna and collaborators.
So
And
can I
yes,
just ask,
yeah.
so this is a different definition of Markovianity now compared to the previous slide, because there's no semi-group structure here.
There is no,
And previously we had it for semi-group structure.
yes.
So we want to work with this.
So of course,
This more general.
because it is
definition.
more general, just what people usually call Markovian semi-group is just a special example of that, right? Because for Markovian, what we call Markovian semi-group, this two-parameter family is nothing but L, well, maybe like the T minus S times L, right? And of course, you can extend this definitions of P and CP divisibility to K divisibility, right? We may call original map to be K divisible if the corresponding family of these propagators is K positive and trace preserving. And of course, if K is larger than L, then K divisibility immediately implies L divisibility. So CP divisibility implies P divisibility, right? Okay, so if we denote by TK set of K divisible dynamical maps, then of course we have this simple hierarchy, right? That we have complete CP divisible, which are Markovian, then D minus 1 divisible, and so on. D1, which are P divisible, and then the set of all dynamical maps. Okay. There is in the literature there is another influential concept of Markovianity, which was proposed essentially at the same time by these people, Royer, Lane, and Pillow, and they relate Markovianity to the following property of an original dynamical map, lambda of t. Then you pick up two arbitrary initial states, rho 1 and rho 2, right? And essentially you check what happens to distinguishability of these two states in the course of time, right? And they call evolution to be Markovian if and only if this quantity, they call it information flow, enjoys this property. So whenever this inequality is violated, they interpret this violation as a backflow of information from the environment to the system, which is a clear sign of memory effects or quantum non-Markovianity. Right? But look, P divisibility immediately implies this property, because P divisibility implies that implies monotonicity not only for Hermitian traceless operators, but for all Hermitian operators. So it's stronger than this property. So CP divisibility is stronger than P divisibility, and P divisibility is essentially stronger than this property, which is no information backflow. Just for clarification. But because of this suggestive interpretation, still a lot of researchers just use this concept of Markovianity as a monotonicity of, essentially monotonicity of distinguishability of two arbitrary quantum states. And actually, if the map is invertible, you can very easily prove the following results, that the map is K divisible if and only if monotonicity property holds for essentially all Hermitian operators, right? So for invertible maps, divisibility is equivalent to monotonicity property, right? For any x. And interestingly, because if you go to laboratory and talk to your colleagues, they're not very happy to when you start to explain complete positivity. For example, positivity is enough. So we observe the following simple property is that complete CP divisibility actually is equivalent to the following properties, that the second tensor power is P divisible. Okay. What happens to what happens if the map is not invertible? Actually, this problem, how to relax invertibility, was posed by Francesco and Nila more than 5 years ago, and their analysis is very much based on this distinguishability of quantum states. So if you want to learn more, just wait for Francesco talk this afternoon. Okay, if the map is non-invertible, as I said, divisibility is not guaranteed. You require the following condition for kernels of the map. So the propagator then is uniquely defined only on the image of lambda s. Of course, you can using the concept of generalized inverse, which is again non-unique, you can extend to the entire B of H. But now the question is, could you find proper extension? I mean, positive and completely positive and trace preserving. So in this case, monotonicity of the trace norm implies that the propagator is K positive and trace preserving, but only on the image of lambda s, right? The problem is, could we find K positive trace preserving extension to the full algebra B of H? And as you know, there are several so-called extension theorems. The most known is celebrated Arverson extension theorem, which says that if your map is defined on a operator system in B of H, right, and this map defined on M is unital and completely positive, then there exists unital completely positive extension. It works for CP. In general, does not work for maps which are only positive. Another elegant, interesting theorem of that kind is due to Anna Jęcowa. She proved that again, you have a map which is defined only on a linear subspace of V of H, which is spanned by positive operators. And then she proves then, so if the original map is CP, then there exists CP completely positive extension. However, this result says nothing about trace preservation, only about complete positivity. So the question is, could we have both complete positivity and trace preservation? And what we proved is that if this monotonicity property is satisfied, then you can define a propagator, which is CPTP only on the image. And using Jensova extension theorem, you are sure that this propagator can be extended to a completely positive map on the entire B of H. However, this extension does not guarantee that extended map is trace preserving.
H is finite dimensional.
Right.
You say that it's not unique.
It's not unique. It's not
Then you
unique.
choose it in such a way that it's trace preserving.
We don't know. Open problem, all right? We don't know. We know a subclass maps for which we can check that there exists among this infinite possible extensions. We can find extension which is trace preserving. But this is very special class. Well, the map is commutative, so any two maps at time t and t1 and t2 they do commute, and the map is well this assumption is rather is diagonalizable, but this is essential. Okay. However, as you know, the dimensional system is very special. So actually, we prove that if D is 2, the result is universal. So it is not important whether or not the map is invertible, right? If it is, the map is CP divisible if and only if monotonicity property is satisfied for n x. And actually, the proof is based on the following observation that the image of the map for the qubit scenario cannot be three-dimensional. It is four-dimensional, generic case, the map is invertible, or two-dimensional, or one-dimensional. If it is one-dimensional, actually projects to some quantum state, time-dependent quantum state omega. So the most interesting case is two-dimensional scenario, but in this case we use celebrated Alberti-Ullmann observations that if you have two pairs of states, rhos and sigmas, and you ask whether there exists a quantum channel connecting rhos with sigmas, then the existence is governed by this theorem. The channel exists if and only if the following inequality is satisfied for any positive t. But look, that this inequality can be translated into the following one, and actually that one relates distinguishability of rhos with priors p1, p2, and sigma with prior probability p1. Right. Okay. So now let me try to characterize the very notion of divisibility in terms of the corresponding time local generator. So let us assume that our dynamical map, lambda of t, enjoys this linear master equation with time-dependent generator. How to characterize divisibility of lambda in terms of some particular properties of the generator. And actually, it's very easy. Using the properties we already learned from the very structure of Markovian semigroup. So P divisibility is controlled by this property, where P is again arbitrary rank 1 projector in the Hilbert space, right? And CP divisibility, well, to control CP divisibility, you have to extend L of T by D-dimensional identity. And essentially, it's not difficult to prove that in that case, LT has to be of GKLS form for any T, right? So CP divisibility is controlled by well-known property. L of T is just time-dependent Lindbladian. However, if the property to be just P divisible or K divisible is very hard, right? It is this property. The problem is that you have to check it for all rank 1 projectors. Okay, so let me illustrate the difference between P and CP divisibility in terms of properties of corresponding time-dependent generator, just on the very simple example. So consider the following qubit generator. Sigmas are just Pauli matrices, right? So CP divisibility is very simple, right? All time-dependent rates have to be positive, right? This is just GKLS condition. Now, however, in this case, P divisibility, again, it's not difficult to show that in this very simple case, P divisibility is essentially equivalent to BLP, Breuer-Lane-Pillow condition. Remember, this is condition for no information backflow, right? And it is controlled by the following conditions on rates, gamma of T, which is of course weaker than condition for CP divisibility. Now you require that, well, you can have some gammas which are temporally negative, right? But still may enjoy this property. And somehow extreme scenario was realized by the following example. Well, you may consider quite artificial, but the goal was to find a scenario in which one of the rate is never positive, right? It's always negative. But still, apart from, well, still having one of the rate which is always negative, it's very easy exercise to check that the evolution is well defined, completely positive and trace preserving. Not only that, enjoy this property. It's P divisible. Of course, it's not CP divisible because one of the rate is negative, but enjoy this property. Yes.
I guess that's the question. If you replace the sigma case by arbitrary sigma case in higher dimension, the same Pauli matrices, but copies of them, do you still have an analysis for this kind of semi-groups?
Yes. Yes, we have.
Very good.
Yes. We call it generalized Pauli channels. Well, yeah, we have. Well, you may consider this rate very artificial. However, what we also observe that, let me denote that kind of generators by L of K. Let us consider the following very simple evolution. Just take a convex combination of two Markovian semigroups, right? One generated by L1, right, and the second by L2. And if you find the corresponding generator, actually the generator is governed by that kind of gammas, right? So very simple evolution, just a complex combination of two Markovian semigroups gives rise to quite strange well, transition rates. Moreover, this example clearly shows that maps which are CP divisible, the set of maps which are CP divisible is not convex, right? Because you take Markovian plus Markovian, highly non-Markovian, right?
There's no operational interpretation of such a convex combination, no? I mean,
You can find, no, you can find.
You can say,
Yes.
you flip a coin at the beginning and then it's long time memory. Which branch you go?
No, you can couple your system to ancilla, and start with ancilla, classical state of ancilla. Somehow, you know this. Okay, let me go to the next slide and I will explain. Because, well, observing this very simple relation between, well, simplicity of evolution and quite complicated structure of the rate, we just ask simple question. But what happens if we take just arbitrary convex combination of these guys, right? Then we observe that it is always, so we have a probability simplex. We observe that it is always P divisible for any point from the simplex. However, it is CP divisible only on the tiny region on the simplex. And actually, that kind of evolution can be simply realized. You couple to ancilla, and you start with ancilla, which is which is represented by classical state, which somehow represents this probability distribution. It can be done, right? So it's not purely artificial. Okay, another simple example, but actually this example somehow describes majority of qubit evolution studied so far in the literature, because somehow it encodes the most important physical processes. That one is responsible for pumping from the ground state to excited state. This is just dissipation from the excited to the ground, and this is just decoherence with respect to sigma z phases. Again, CP divisibility, all rates are non-negative, right? Gamma plus, gamma minus, and M gamma d. Now P divisibility requires that only rates governs pumping and dissipation are non-negative. Gamma z can be, sorry, these are non-negative. Gamma z can be negative, but not too negative, right? It's constrained by Z1, this condition. And in this case, this condition for no information backflow is different than condition for P divisibility. Right? It's weaker, because if this condition holds, this condition immediately is satisfied, right? Gamma plus, gamma minus positive implies that gamma plus gamma minus is positive, and this condition immediately implies that one, right? So this simple example shows essential difference between all these three Markovianity conditions. Here you require complete positivity of propagators. Here you require only that divisibility monotonically decreases in time. Okay, so my next topic I wanted to discuss is related to quantum processes. But now I see that my time is quite limited. No? Okay, let me try to at least to say something. Okay, so, well, you know that if we have a classical stochastic process, we find in terms of, well, you have a random variable, you compute probabilities to have x1 at t1 and x2 at t2 and so on. Then this infinite hierarchy of endpoint probability distributions enjoy so-called Kolmogorov consistency condition, which essentially means that, well, you have endpoint distribution and you sum up over j outcomes. This gives you n-1 point probability distribution, and vice versa. If you have a family of probability distributions enjoying this property, then, as Kolmogorov proves, there exists a underlying stochastic process which gives rise to the hierarchy of probability distributions. And the process is Markovian, and only if this condition is satisfied, right? And in this case, as you see, essentially the endpoint probability distribution is fully controlled by 1 point probability distribution and transition matrix P, right? Okay. Okay, well, so with Kolmogorov consistency conditions are just, well, infinitely many constraints for probability distributions. However, if we know that the process is Markovian, then this infinite hierarchy essentially reduces to these two conditions, right? For 1 point probability distribution and this transition matrix. So essentially, this is one famous Chapman-Kolmogorov condition for the transition kernel. Okay. So now let us move to quantum scenario. So let me consider a composite, well, the system which is coupled to the environment, or well, I call it bus now. So we have a unitary evolution of the total system, right? And let me fix an orthonormal basis in the Hilbert space of the system. These are corresponding rank 1 projectors. So we have a family of completely positive maps with, well, this simple cross representation. And then we immediately define family of probability distributions, right, using this, well, essentially Born rule. Right, so we start, this is initial state. We evolve, measurement, evolve, measurement, and so on. So this gives rise to legitimate family of endpoint probability distributions. But in general, this family does not enjoy the Kolmogorov consistency conditions, right? So following this nice review paper, you may call a quantum process defined by this formula and classical if Kolmogorov consistency condition is satisfied for any n from up to n, right? And eventually you call it classical if it is n classical for n. Well, of course, this very notion of classicality is defined with respect to orthonormal basis we fixed at the very beginning. It is classical with respect to that orthonormal basis. Okay, and well, another obvious definition is definition of Markovianity of the process. So again, this is the definition of our quantum process. And essentially, we repeat the classical definition of Markovianity. Again, you may call it N-Markovian if Markovianity condition is satisfied for n from 1 up to capital N. And eventually, you may call it Markovian if the process is N-Markovian for N. Again, the definition somehow is constrained into the fixed orthonormal basis. Okay, so given a process, you may try to check whether the process, well, given a process which is defined with respect to a fixed orthonormal basis, you may ask whether the process is classical, and you may ask whether the process is Markovian. And now it is well known that actually the Markovianity can be translated into the following relation, that this endpoint probability distribution, which is defined using the unitary evolution of the system plus environment, can be equivalently represented using, and you remember that we measure only a system, right? Nothing happens to the bus. We measure x1 at t1 and so on, right? Markovianity essentially means that this probability distribution can be recovered, but only using the reduced evolution of the system and measurements on the system, right? Very often that relation is called quantum regression formula, in particular in quantum optics, right? This was already well known long ago. So Markovianity is a quantum regression. Well, as there is a fancy way to reproduce this result, you may define so-called process tensor, or some people call it quantum comp. There is a beautiful review of this concept. Well, Kavan Modi really published a lot of papers on that. So they define a process tensor, right? So the process is Markovian if and only if the process tensor, in a sense, is divisible. You can split it into evolution, measurement, but evolution of the system itself, right? Start with the initial state of the system, you evolve, measure, and so on, right? This is Markovian. Okay, so in general, the given quantum process is neither classical nor quantum. Well, it could be classical, but not Markovian. It can be non-classical, but Markovian. It can be both classical and Markovian, right? So we just ask that kind of questions for two particular models, already well studied in the physical literature. One is so-called amplitude damping. Well, both are qubit dynamics, but can be easily generalized for actually arbitrary dimension, finite dimension. So one is amplitude damping, and the other one is well-known pure dephasing. So amplitude damping, this is the evolution of the system, which is coupled to the bosonic bus. So this is the Hamiltonian. Well, this is the qubit. So this is an excited state. This is a ground state, right? This is a free boson Hamiltonian, and this is the interaction, right? This is the interaction. This f of omega, form factor f of omega somehow, controls the coupling between a qubit and the omega mode of boson field. And if you start with a vacuum in the boson field, then you can essentially solve the Schrödinger equation for the total system and eventually find the reduced evolution. So this is a formula for the reduced evolution. So the evolution of the qubit system, right? And and as you see, it's very simple and it is controlled by one complex function A of t, right? And this function enjoys the following time non-local equation. And this memory kernel is defined in terms of this form factor f of omega, right? So all the dynamical properties of the map are encoded into the properties of this A of t function. So in this case, well, because the evolution is very, very simple, actually in this case, yes?
Yes, you have.
5 minutes is fine, okay. So the evolution is very, very simple. In this case, it's two notions coincide. P divisibility coincide with P divisibility, and it is controlled by this monotonicity property, right? Again, A of t is this function which controls the evolution. Okay. Okay, but again, this is a very concept of Markovianity, which is defined on the level of dynamical map. Now you may ask the question, but what happens if we define a process, right? We sequentially measure the system, define a tensor process, and is it Markovian? Is it classical? So the quantum process is Markovian for any choice of measurement, if and only if, well, essentially the coupling is flat, right? Does not depend on omega. So all frequencies couple in the same way to the system. Moreover, in this case, reduced dynamics is not only CP divisible, it's Markovian semigroup. Well, it is well known, right? If the coupling is flat, you get Markovian semigroup. Okay. Now, if we assume that the process is Markovian, so the coupling is flat, then it is classical if and only if we measure with respect to the essentially eigenbasis of sigma z, right? So we measure the measurement basis coincide with the original basis, which essentially represents the evolution. I mean, ground and excited state of the qubit. However, if you measure in another basis, it is not classical. Right? The process does not satisfy Kolmogorov consistency condition. Okay, and then we study another system, so-called dephasing evolution, which was also presented yesterday in connection to GNS symmetry. So you have a Hamiltonian of that form. Again, you fix a basis in the Hilbert space of the system. These are rank one projectors. Okay, and in the qubit case, you get very simple evolution. Right, this is usually called dephasing function phi of t, which is defined in terms of, well, if these two, you have two Hamiltonians of the bus, right, H0 and H1, and the state of the bus. So again, everything is very simple. All dynamical properties are controlled by a single function phi of t. Okay. And again, the same question. Divisibility property. again, CP and P divisibility coincide. And as in the previous example, they are controlled by monotonicity property of phi. Right, so knowing phi, the evolution is Markovian in the sense of dynamical map, if and only if phi enjoys this monotonicity property. What about the corresponding process tensor? Well, the evolution has this form, right? Or this guy's, well, this is a universal for any dimension, right? These guys are defined as follows. And let me define small u, just tracing, computing the trace of this operator. So, Kolmogorov consistency conditions are equivalent to infinite hierarchy. Here I just displayed two members of the hierarchy. Generalization is obvious. So look, you compose two u's, right? From time t0 up to t1 and from t1 up to t4. And this is the same as multiplying. Okay, so the trace of composition is essentially the same as you multiply the traces, right? And if you have three, and you compose, and then you take a trace, it's the same as take a trace and multiply, and so on, right? So if these two is, you can check everything. So if the measurement, again, if the measurement basis coincides with the phasing basis, then the quantum process is trivially classical. It's trivial, right? This is a formula for the family of probability distributions. Okay. Now, what happens if you measure in a basis which does not coincide with the phasing basis? And what we found is that if the dephasing basis and the measurement basis are mutually unbiased, so they enjoy this property, and the initial state of the system is diagonal in the original dephasing basis, and the process is classical if and only if the phasing function is real. Last slide. And actually, this analysis of amplitude damping and phase damping can be generalized for arbitrary dimension, which we did with Davide Plonigro recently. Okay, thank you very much.